Welcome back, everybody. This is the last section in Chapter 6. So Section 6.6 will be working on seeing how you can use the normal distribution to approximate the binomial distribution that we'd studied in Chapter 5. So some fine print here, I want to kind of go over that. As I'd said, we'll be using the normal distribution from Chapter 6 to approximate the binomial probability distribution from Chapter 5. And the reason why we might want to do that, like why would you even bother, is that for some problems, the computations involved with the binomial distribution are just basically too hard. And so using a normal distribution approximation, as we'll see, it can be a lot easier, more manageable for us to deal with. So that's the motivation behind it. There's, of course, some requirements that we need to pay attention to when we're going to do it. We need to have NP to be at least 5 and NQ also to be at least 5. So for a proportion P, if those two conditions are satisfied, the probabilities from a binomial distribution can be approximated reasonably well using a normal distribution, where the mean, the mu for our normal distribution, will be NP, and our sigma for the normal distribution will be the square root of NPQ. So there's our mean and standard deviation. There's one piece that you're probably going to find a little bit tricky, and that is going to be this idea of a continuity correction. And what that is about is this. The binomial distribution was a a discrete distribution, and so we used it to count whole number outcomes, getting like 3 heads in toss of a coin or 4 heads in tosses of coin, not like fractional outcomes. But the normal distribution is continuous distribution, and so we need, if we're going to use the continuous normal distribution to approximate the binomial distribution, there's a little adjustment to make, which we'll talk about when we get there. And that's this idea of a continuity correction that is referred to right here. So before we get into all that, though, it's been a little while, so I want to review the binomial distribution with you, and then we'll actually see about how to use the normal approximation. Okay, so the background is a binomial distribution has a fixed number of trials. The trials need to be independent, and they have 2 possible outcomes, which we'll consider to be success and failure. And as a reminder, those don't have to be actually positive things, right? You could think of, like, a mechanical part wearing out as being a success, where ordinarily you wouldn't think of such a thing. So just think there needs to be 2 possible outcomes. That's why it's bi and binomial, 2 possible outcomes. And then the probability of success has to remain constant. We had specific meanings for certain symbols. N is the fixed number of trials. If you're tossing a coin 10 times, or you're taking a quiz that has 8 questions, or whatever it is, the number of trials there are. X is the specific number of successes that we're trying to find in N trials. P is that constant probability of success that you'd find in 1 trial. Q is then the probability of failure. So Q is the complement. And so it's going to be 1 minus P. So let's try it. Suppose that we have a lot or batch of 1,000 computer chips, and it's known that 12% are defective. If we're going to pick out 8 chips, we want to know the probability that 3, that is exactly 3, are bad. So the formula involves a combination. So C for combinations. Out of 8 chips that are chosen, we're finding 3 to be bad. And then the probability of success, here the success is getting one of those defective chips, that occurs with probability of 0.12, and we're looking for 3 chips to be defective. Then what's about the other 5 chips? Well, they're going to have probability 0.88. That is 1 minus 0.12. And each chip then has an 88% chance to not be defective. And that has to be true of the remaining 5 chips. Then we will go ahead and calculate that. See what we get. All right, so I'm getting about 0.051. All right, so that's an example of the binomial distribution. So what we want to do next is start thinking about how we can use the normal distribution to approximate it in cases where that is not more complicated than it was just now. So we need to look at that continuity correction I'd mentioned. So here we have a picture of the normal distribution kind of superimposed over a binomial distribution. And the normal distribution is a continuous distribution. The binomial distribution is discrete. So taking a look at, for example, if we wanted to know the probability of getting fewer than 6 successes, we're looking in the upper left here, less than 6 would be 5, right? 5 or fewer. So we want to think about what numbers would round to 5 if we're looking at a continuous interval of numbers. That is, the number 5.8, for example, would round to 6. Which numbers would round to less than 6, that is 5 or fewer, would need to be 5.5 or less. X has to be less than 5.5. Because anything that is 5.5 or less is going to get rounded down to 5. For more than 15 successes, more than 15 would be anything that would be 16 or higher. So that would be requiring our X to be at least 15.5. If we just use, when we look up values using the normal table here, if we just use our X of 15, we would miss the part that gets rounded to 15. That is the numbers 15 to 15 and a half. So we have to go all the way up to 15 and a half. If we wanted exactly 14 successes, let's say that we wanted exactly 14 successes, you want to take a look at the bar here and think about what's going to get rounded to 14. Numbers that get rounded to 14 would be the numbers between 13 and a half and 14 and a half. If you pick any number between 13 and a half and 14 and a half, that'll get rounded to 14. So we'll need X to be greater than 13 and a half, greater than or equal to 13 and a half, and less than or equal to 14 and a half. So that will be the correction that we'll make for continuity. All right, easier to see once we try it. Okay, so recapping the requirements that we'll need to have, as always, a simple random sample of size n. Our proportion of success is p. We're doing n independent trials, and the probability of success is p. We need np to be at least 5 and nq to be at least 5. Those are the requirements. If we do that, then our normal approximation will have mean mu, which is going to be np, and standard deviation sigma, which is the square root of npq. So let's first just check and ensure that some requirements are satisfied. So that's what we'll do in this first example. Here it says decide whether you can use the normal distribution to approximate x, the number of people who reply yes. If so, then find the mean and standard deviation. And if not, you don't have to. Here it says 37% of people in the US say they always fly a flag on the 4th of July. You randomly select 15 people and ask each if he or she flies a flag on the 4th of July. So for this, our n is going to be 15, because you picked out 15 people. Our probability of success, it says 37% of people, so that's 0.37. Our 0.37 is going to be our probability of success. So Q, which is 1 minus P, will be our probability of failure, and so is 0.63. So then our NP, we needed that to be greater than 5. Let's see what it is. 15 times 0.37. 15 times 0.37 works out to be 5.55, which is greater than 5. So that's good. And then we also needed NQ, which is going to be 15 times 0.63. And if you think about it, that has to be greater than 5 also, but we'll get the actual number, which works out to be 9.45. And so that's going to be greater than 5 also, so it's okay. So the second part of the question, we're to find the mean and standard deviation. Fortunately, the mean, you've already done it. It's NP, and so that will be 5.55. Then the standard deviation is the square root of NPQ. And so that will be 15 times 0.37 times 0.63. So let's see what that is. So that's about 1.87 for the standard deviation. So we first check to make sure that NP and NQ are both bigger than 5. That's what justifies our usage of the normal distribution to approximate the binomial. And then we'd calculated the mean and standard deviation. Okay. For the second part, it says 93% of people in the US want the national anthem to remain the same. You randomly select 65 people in the US and ask each if he or she wants the anthem to remain the same. So as before, we'll start by grabbing the N, the P, and the Q. There were 65 people. It said 93% want the anthem to stay the same, so that is our P. And so Q is 1 minus 0.93, so it has to be 0.07. So here our NP is 65 times 0.93. That'll be bigger than 5. Let's see what it is. That's going to be 60.45. So that's okay so far. And then NQ is going to be 65 times 0.07. And that's 4.55. So unfortunately, that's less than 5. So we wouldn't be able to continue and use the normal approximation to the binomial for part B. So that's the first part of any problem where you're thinking of using the normal to approximate the binomial. In our next example, we will actually do it. So we'll do it in a couple of steps. So the story for this, it says 21% of people in the US say they are confident that passenger trips to the moon will occur in their lifetime. You randomly select 200 people in the US and ask each if she or he thinks passenger trips to the moon will occur in his or her lifetime. So for this one, our N is 200. That's the number of people surveyed. It says 21% of people have this belief, so that will be our P. And so Q will need to be 1 minus 0.21, 0.79. Okay, for part A, it says, what is the probability that exactly 50 people say yes? And we're told to use the binomial formula to do this. So that is going to be C and X, and then P raised to the X power, and Q raised to the N minus X power. So here's C, 250. 50 people are, we want 50 people to say yes. The probability that someone says yes is 0.21. That is to occur 50 times. The remaining people, there's a 79% chance that they say no, and that has to be 150, right? Notice that those two exponents have to always add up to the total number of people. 50 plus 150 equals 200, right? So let's see what we get for that. Okay, I took my calculator a little while. Depending on your calculator, it might overflow if you try to do this. Also, you're going to want to keep intermediate results in your calculator for as long as you can, because there's some pretty big numbers for that combination and then pretty small numbers for the two powers. So it could be off by quite a bit if you're rounding. All right, so it ends up being about 0.026. All right, so now it says we want to know the probability that exactly 50 people will say yes, and this time we're going to use the normal distribution, or sorry, normal approximation to the binomial distribution. Before we do that, we should make sure that we're actually permitted to do that. So our NP is, N is 200 times P, and that's 42, which is bigger than 5, so that's okay. Our NQ is going to be 200 times 0.79, which will also be bigger than 5. So that's 158. So that's okay. So we're justified in using this normal approximation. All right, so now to actually get this done, the mean, we need the mean and standard deviation. So the mean is NP, which we calculated, that's 42. The standard deviation is the square root of NPQ. And so that is square root of 200 times 0.21 times 0.79. And that works out to be 5.76. Okay, so now our mean was 42. And so we wanted the probability of getting exactly 50. And so again, remember that we're going to be using the normal distribution to approximate a binomial distribution. So we can't get the exactly 50 outcome, because the probability on a normal distribution of getting exactly 50 would be 0. So we need to think about what numbers would round to 50. That is, we need the probability that x will lie between 49.5 and 50.5, because those are going to be the real numbers that would round to 50. So we'll be calculating a couple of z-scores and then looking up some probabilities in the table. So we'll do that here in just a moment. All right, so I've calculated the z-score for 49.5. That will be 49.5 minus the mu over the standard deviation. That gives 1.30. And then I also did it for 50.5, getting 1.48 for the z-score. Looking up those probabilities in our standard normal table, the probability that z will be less than 1.30 is 0.9032. And then for less than 1.48, it's 0.9306. So basically, we want the area under the curve that is approximately the area inside this rectangle. And so that will be the difference of 0.9306 and 0.9032. And that's 0.0274. All right, so that's 0.0274. We calculated it using the binomial formula and we got 0.026. So a natural question at this point is, why would we go to all that trouble when the binomial formula was pretty short, right? And on the part B, we had to do the continuity correction thing. We had two different z-scores. We're looking at values in a table and everything. Two reasons. One is, let's say that your calculator is not able to do this combination, 200 choose 50, or 0.21 raised to the 50th power. That's going to be hard. There's also a historical reason, and that is, okay, back in the days where people didn't have like computers and things that could do all these calculations, this part, although you wouldn't necessarily want to do this by hand is going to be way easier than doing the part A by hand. The second reason is that the way that we did it in B works better for situations where there's more than one value. In part B, it was exactly 50 people, but what if it was at least 50 people? So if it was at least 50 people, let's go ahead and draw that out. If it was at least 50 people, then that is anything from 50 upward. And the thing is that there were how many people surveyed? 200. So we know from our work in chapter 4 with probability that if it's going to be 50 to 200, we'd have to find the probability of exactly 50, exactly 51, exactly 52, and so on, all the way up to 200, and add together all those probabilities. Often with at least or ideas like that, we might think of the complements rule. So we think, okay, well, let's try the complements rule. Say, okay, if we don't want at least 50, then say the complement is less than 50, which is 49 and below. That would be 49, 48, 47, 46, 45, 44, and so on. That's a little better, but you're still having to figure out 50 probabilities, right? 0 through 49. So that's more work, much more work. And so here our normal approximation is going to be really helpful. So before we saw that our mean was 42 and our standard deviation was 5.76. So we don't have to figure out probabilities for 0, 1, 2, 3, 4, 5, and 6, all the way up to 49 and add those, right? Instead, we're going to use the approximation. So if we want at least 50 would be 50 or more. So that would be anything that is higher than 49.5. Anything that is higher than 49.5 is going to get rounded up to 50. So we'll want the part to the right of 49.5. That is probability that X is greater than 49.5. So let's get a Z for that. Our mu is 42. Our standard deviation, 5.76. All right, so that's 1.30. I should have known that. We did that earlier. Yeah, that was up there. Oh, well. Okay, so we did get the probability for that. That was 0.9032. So that worked out to be 0.9032. That's the area to the left. We wanted the right tail though, right? And so we'll take 1 minus 0.903. 1 minus 0.9032 is 0.0968. All right. So that's what the probability works out to using the normal approximation. I went ahead and had calculated this using R, which is not, we haven't used R much at all in this class, but, and that's fine. But just so you know, the exact answer works, or closer approximate answer works out to be about 0.098. So we're only about 200ths off, or 2,000ths off actually. So, that's the end of that example. So you can tell by looking at this that this would be a good example of where we would use the normal approximation to the binomial, because figuring out 50 separate probabilities and adding them all up would be harder. Of course, I did it on the computer and it was pretty fast, but if you're doing it by hand, the approximation is going to be much quicker. Okay, all right, so more examples. So here it says a survey reports that 39% of internet users clear their browsing history often. You randomly select 200 internet users and ask whether he or she clears the browsing history often. So our N is the 200 people. Our P, probability of success, is 0.39. So our Q will be 1 minus 0.39, and that's 0.61. All right, so here it says, what is the probability that exactly 82 users will say yes? We're to use the approximation. So we had better check and make sure that we're justified in using that approximation. So it's 200 times 0.39. And that works out to be 78, which is definitely more than 5. And then NQ will be even bigger, right? It's 200 times 0.61, and that's going to be bigger than 5. So we are okay. We figured out the mean. As part of doing that, it worked out to be 78, because that is going to be NP, and so it's 78. We'll need also the standard deviation, which is the square root of NPQ. So that's 200 times 0.39 times 0.61. And that's about 6.9. I've rounded there, 6.90. So our mean was 78. We wanted exactly 82 users. Okay, so again, we'll have to use that correction. So which values will get rounded to 82? It will be anything that is between 81.5 and 82.5. Values of x between 81.5 and 82.5 will round off to 82. So we're going to need z-scores for those two n's, and we'll end up subtracting again. So let me go ahead and calculate that for you. All right, so for 81.5, we got a z-score of 0.51. For 82.5, we got a z-score of 0.65. So then, using our table, the probability that z will be less than 0.51 works out to be 0.695. And then the probability that z will be less than 0.65 will be 0.7422. And so we want the area of that strip. So we'll have 0.7422 minus 0.695. So that's 0.0472. Okay, now we're going to have the exact answer using the binomial distribution. So since we're looking at just a single value, this is going to be less work. So out of the 200 internet users, we're looking for the probability that exactly 82 will say yes. The probability of success was 0.39. That's to occur 82 times. And then the failure was 0.61. And then that has to occur 118 times. So let's go ahead and calculate that. Again, you may have, your calculator rather, may have a little trouble with this, but hopefully not. Okay, 0.0484. All right, so here we were good. We're off by like 1/1000th in using the approximation, so that's pretty good. All right, so now we want the probability that fewer than 65 will say yes. So again, this one would be one that would be tough to do using the binomial distribution, because fewer than 65 would have to be 64, 63, 64, and so on, all the way down to 0. And so that would just take far too long. So we're going to use the approximation. So again, here our mean was 78. We had calculated that back here in part A. Our mean was 78. Our standard deviation was 6.90. Okay, and we want to be fewer than 65. Fewer than 65 is actually 64 or less. You have to think about what would be rounded to 64 or what wouldn't be rounded up to 65. That would be anything that is less than 64.5. Anything higher than 64.5 would get rounded up to 65. We want fewer than 65. 65 isn't fewer than 65, and so we have to make sure we stay lower than 65. 64.5 is where we need to be. So that's what we want. So as before, we'll need a z-score. So we have our x, 64.5, our mean, 78. Our standard deviation was 6.9. So that works out to be negative 1.96. And then we'll appeal to our z table and get 0.025, just about. Okay, so that's it, 0.025. All right, and then our last piece, we want to know the probability that between 80 and 90 people will say yes. So between 80 and 90. So we have to think about what values are going to get rounded to something between 80 and 90. It has to be greater than 79.5 and less than 90.5. Values in that interval are going to get rounded to numbers in between 80 and 90. So that's what we need. So we're going to have a z-score for each one. And then we'll end up subtracting as we did before. So let's go ahead and do that. All right, so I've gotten a z-score for 79.5 of 0.22. And so we'll need the probability that z is less than 0.22. And once again, going to our z table, 0.22, that will have probability of 0.5871. And then for 1.81, it will be 0.9649. So then we want that area of that strip, basically. And so that will be the difference of these two. That works out to be about 0.3778. And that's our final answer to that question. All right, so now we will go on to our last example. So here's the story. It says electronics components produced at a factory have an 11% rate of defects. Out of a batch of 1,000, a sample of 50 is taken. We want to know the probability that more than 7 are defective. So it doesn't explicitly say that we should use normal approximation for this, but we're going to. So we want to know the probability that more than 7 are defective. So the first thing that we should do is check and see if we're justified in using that normal approximation. And then we'll go ahead and do it. So n is 1,000. No, actually our n is 50. And then our p is 0.11. And our q is 0.89. So NP is 50 times 0.11. Which is 5.5. And then NQ is going to be 50 times 0.89, which is going to be bigger than 5. All right, so we're justified in doing this approximation. So our mean, mu, is going to be NP, and that was 5.5 as we saw. Our standard deviation will be the square root of NPQ. So N was 50. Our P is 0.11. And our Q is 0.89. So that's about 2.21. Okay. So our mean was 5.5. We wanted to be more than 7. So that means that using our continuity correction, we can't just use a 7 here. It needs to be 7.5. All right, so z-score. That's 0.90. Looking to our z table, the probability that z will be less than 0.90 is 0.8159. That was the left tail. We actually want the right tail. So that'll be 0.1841. All right, so that does it for the end of section 6.6. Let me know if you have any questions and have a great day.